Alright, so question number 10. Okay, so for this question, we're asked the following. Two wires lie perpendicular to the plane of the paper and equal electric currents pass through the paper. So we have two wires that are lying perpendicular to the paper, and we have equal electric currents. Point P is equidistant from the two wires, so at the same distance from each wire. All three components create what looks like an equilateral triangle. So they're in a triangle format. So they look something like, let's say we had one wire, or we'll say X, that means the wire is going into the page, and then we have another wire that is also going into the page. So when there's two kind of formats to represent into the page and out of the page. Into the page is like this, out of the page is like this. So when you have this, you know that the wire is going out of the page and the current is coming at you, versus when it's an X, you know that the current is going into the page. Okay, we'll continue on. So P is an equidistance and they form kind of an equilateral triangle, so we'll say point P somewhere over here. So number 1, construct a vector diagram showing the direction of the resultant magnetic field at point P. Explain your reasoning. If the current in both wires were instead directed out of the plane of the page, show the resultant magnetic field at point P. So essentially, what we'd have to do is use kind of the right-hand rule to figure out the vector for the magnetic field. So let me just let me just double check something over here. Alright, so essentially to figure out the direction of the magnetic field, what we'd have to do is kind of the right hand rule. And to do this, you would essentially kind of, if you just take your right hand, and when you're looking at, let's say this, you would point your thumb into the page and look at where your fingers are rotating. So if we point our thumb into the page, we can see that our fingers are rotating in this direction for the first wire. So this is wire 1, we'll call it wire A, and this is wire B. So for wire A, we can see that the magnetic field is acting in this direction. So whenever I kind of think about what direction, so B here represents magnetic field. So if we take just the perpendicular line over here, so if we had some line kind of like that, and say this is at a right angle, so this isn't really at a perfect right angle. Let me just redraw this quickly. So if we had something like this, you can see that using the right hand rule, so you take your hand, you point your thumb into the page. So for me, it's kind of going this way. So and your fingers curl around to kind of, they curl in this direction, and you can see that the tangent here from this line will point in this direction. Similarly, if we did the same thing for this one, you can see that, so this isn't the best equilateral triangle, but essentially you'd see that it would point in this direction for B, B. And there's a right angle over here. So you do the same thing with the right hand rule. Your thumb would be pointing into the page, your hands curl around to show you that it's in this direction. And then since these are equal electric currents, we know equal electric currents will give us equal magnetic field. So each wire provides an equal magnetic field. So we can see from this, each one will have a Y component and an X component, and a Y component up here and an X component. Since B, the magnitude for the magnetic field of the first wire and the magnetic field of the second wire are equal, we know that the y component cancel out, because here we have a positive y. Let me just draw a coordinate system, so we'll say that something like this, x, y. So upward is positive, and then downward is negative. These cancel out, and then we have negative x plus negative x. So we know the result will be something like this, and that will be the result. So we'll call this net, Bn. And that will be the direction that the magnetic field points in. So let's think about so this is the first scenario. Construct a vector diagram showing the direction of the resultant magnetic field, point P. Explain your reasoning. We kind of went through the process with pointing to this direction. Let's think about, let's say it was pointing in a different direction. So we'll erase this to make some space. I want to keep both diagrams just to show you what I mean. So we have, let's say they're into the page, and we have point P over here. We'd use the right hand rule again, so you'd use your right hand, but this time your thumb is pointing out of the page. So really, when you have your thumb pointing out, you see your fingers will curl in this direction, and it will go this way, because this is the perpendicular or the tangent line. So if we drew kind of just a line like this, the tangent line will be in this direction, and then that's the. Let me draw that all clearer. So this is the direction of the magnetic field for the first wire, and then similarly for this wire, use the right hand rule, and you end up that it's in this direction. These are right angle. So I didn't draw that really very nicely. So really, here, let me draw that a little better. So a dot here. So like that. Is a right angle. And then you have kind of, so this is the magnetic field for this wire, and this is the magnetic field for this wire. So we have same idea, A and B again. So A magnetic field, A magnetic field is this one. B magnetic field is this one. We know that the y components in this direction, and then the x component, the y component, and x component. We can see that there's positive y cancelled out by negative y, since we know equal electric currents means equal magnetic fields, and then we have a positive y, a positive x and a positive x. These add up. We know the resultant would look something like this. So I'm over exaggerating the line, but essentially this would be the net magnetic field of the direction of where it will be pointing at. So I've kind of over exaggerated the line, but it should be a little shorter, but that's kind of the direction it should be pointing at. So here we're not really provided with a solution from the junior tutor, so we'll mark this as the incorrect answer. So, or incomplete solution, no answer present for part A, net magnetic field points to the left if both currents of the wire are going into the page. For part B, net magnetic field points to the right. And we'll mark this as incorrect.